Hi folks, it's Bruce, and you're welcome to my Rocky Mountain Labs here in Colorado. And today we're looking at an HP3320A frequency synthesizer. This unit was produced in 1971. I'm not quite sure how many years it was continued in production, but in 71, the average income was about $6,900. This unit was $1,900. So, you're talking roughly a third of the income of the average worker. So it wasn't a cheap piece of equipment, but it's a true synthesizer, and it can produce frequencies from 0.01 hertz on the dial up to 13 megahertz. Right now, we are putting out 13 megahertz to within 2 or 3 thousandth of a hertz. The specs on this thing are quite impressive. There's 7 ranges. It has a resolution of 1 ppm. Has a frequency vernier that gives you about 30% overrange capability. It's got an accuracy of 0.001% with the vernier out and 0.01% with the vernier in for 6 months after cal. Frequency stability of the unit is plus or minus 10 ppm per year. And this unit puts out 1 volt into RMS into 50 ohms, and that's adjustable. And in terms of dBm, that's 0 to plus 13 dBm. The reason I have the unit is that I have frequency synthesizers that produce really wonderful high frequency signals, but they fail to produce from 1 megahertz down. So I needed a unit that I could dial in quickly, that had accuracy, that was clean, and that could handle the low end. And this unit fit all of that bill. Plus, at 13 megahertz, I mean, you've gone well beyond the regular AM band, which is what, 1.6 megahertz. You're into the short waves, so you're into RF band, and then you go through audio, and then right on down into sub audio, right down to 0.01 hertz. Frankly, the only way that you can read that, at least the only way I can read it, is to put it on a scope with a DC input and take a look at the signal. If I try to pass it through the AC capacitor, no such thing is going to happen. So, but we'll demonstrate that. So bear with me, and we'll continue. Okay, well, while we've got the cover removed to do the calibration, we decided we wanted to give you guys a look at it. The interior is nice and clean. What we see is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sections to the synthesizer, most of which are discrete, combination of discrete and digital components. Generate 20 megahertz and 30 megahertz signals, and then mix them and come up with the differences and so on in the synthesis process. We have the 20 megahertz adjustment point here. We have 3 adjustment points for the vernier control. We have our power supply section. All very nice and neat. No indication of any capacitor discharge or overheated resistors, flames, anything like that. Nice and neat. We're going to button this thing back up and run it through some paces and see what she does. So hang with me. Those of you that have been watching my videos at all have frequently seen me turn to my PTS, either my 160, my 250, or my 500, whichever one I had at the time. I'm up to a 500 now. Because I can depend on them to quickly and accurately generate a very pure sine wave at the frequency desired with extreme precision. And the PTS 500 in this case is I'm able to get down to about 600 kilohertz on the low end, and I can go up to 500 megahertz, and I can do it in 1 hertz steps. But when you want to take a look at frequencies that go below 600 kilohertz, it'll output from 0.01 hertz up to 13 megahertz in 7 ranges. And we're able to do it in hertz up to 1300 hertz, kilohertz. That'd be 120 kilohertz. No, that'd be 12 kilohertz, 120 kilohertz, 1200 kilohertz, finally 12 plus megahertz, 1299. And it will do it with very nice accuracy to 1 or 2 decimal places. Now the low end frequency on this is so good that you can't read it on most frequency counters, because most counters aren't very good below 5 hertz, say. You might find a few that get down to 2. This will go all the way down to 0.01, so you've got to wind up using the DC signal on your oscilloscope in order to be able to even observe it. Like right now I'm running 2 hertz. Let's go to 0.2 hertz. Alright, that would be 0.2 hertz right there. Let's watch that scope a moment. Now you can see we're still tracing the waveform, but 0.2 hertz. And we can go lower. 0.1. And then we can get down into less than 0.1, say 0.05. And so on. So when I want to take a look at the low end of frequency, and I want to challenge my frequency counters to see what their low end is and so on, I rely on my 3320 to do it. So this 3320A is exactly the same thing as my 3320B, with exception that I have a 4-decade attenuator system here, and the A has an amplitude control from 0 to 13 dBm. Other than that, any frequency that I choose to put on this thing is what will be there. Let's put this back. So that'll be 100 hertz. And right now we just... There's 100 hertz. Nice clean sine wave. And at this point we could be reading it on our frequency counter, so no problem. We'll just move from the oscilloscope. Yeah, from the oscilloscope to the counter. Let's get to the right input. There we go. So we have 99.999 to 100. 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 A little variation on the low end. So 13 megahertz is actually getting a fair chunk of the way into the usable RF regions. Let's see, our AM radio, it goes up to about 1.6 megahertz. So we're going almost 10 times that, close to. And that puts us up into the shortwave bands. So, this will cover AM and into the short waves, and it'll take you right down to a fraction of a hertz. So, all at the turn of a dial, and with some accuracy, you can understand where the power of this thing can come in. We're going to put it through some tests, and we'll show you what it does, and then we'll move on. Thank you. Okay, we are right now set to 10 megahertz, and as you can see on the Philips frequency counter, we've got 10 to within 3 thousandths of a hertz. Let's take her down. There's 5 to within 2 thousandths. 1 megahertz. Okay, let's take her to the next level. Here's 100 kilohertz. 99.9999. Let's see, that was 100. Let's do 10. 9,999.997. Let's do 1,000. 999.999. Just kicked in the filter for less than 50,000 hertz, so we'll get a little less noise. Okay, let's there's 900. 800. 500. 100. 99.999 to 100, so within 1,000th of a hertz. Alright, let's this would be 10 hertz. In fact, let's there we go. 10 hertz. 10 with 4 zeros, 9 with 4 nines. So anyway, within a 10,000th of a hertz in this case. Alright, let's take her to 9. There's 9. Let's take her to 5. It's 5 hertz. Now I'm good down to about 3 hertz on this frequency counter. Then we're going to have to do something. We're going to switch to our scope. There's 5 hertz. Let's go to 3 hertz. 2.999, 3 hertz. Okay. Now at this point, I want to move us up to the oscilloscope up here, this Tektronix 2465. Give me a moment, we'll set her up. Alright, we're set to 3 hertz. We're connected to the scope. And I think there's no doubt if you study the trace that we can see we have a sine wave. And right now we're running about 3 hertz on there. Let's take her down to 1. This is 0.1 seconds per centimeter. So we've got 10 centimeters. That would be 1 second in a trace. And as you can see, we're getting roughly 1 cycle across the screen. So 1 hertz. Okay, now we're going to go switch our vernier in. We're going to go down to 0. Here we're looking at a 0.01 hertz signal. And the only scope I had that was capable of displaying this thing with any accuracy was this Tektronix TDS-460A digital. And that's because we had some ranges that I could turn her down to when she was able to match the time for the period of the cycle. And we are running on the dial, it looks like 0.012, maybe 3. I don't know if you can see that or not, but it is outputting a 0.01 hertz. Amazing.